All right. Good evening, everybody. Hopefully you have been lucky enough to catch some of the earlier presentations in this series. And if so, you've heard some people that are doing some really interesting things with code. I'm hoping to convince you today that I too am one of those people. And the work that I do is using code to look at ways in which we might help society deal with climate change. And so the way that I'm hoping to do that is start firstly by explaining to you why it is that we actually need clean energy briefly, although I'm sure you have some idea. Explaining to you why, for the UK, offshore wind power is a very viable solution to that problem. And also showing you how ForeCoast Marine, the software that we build, is beneficial to wind farm developers to solve some of the technical challenges that come from trying to operate offshore wind farms in a difficult climate. And the last thing I'm going to show you is how we can actually scale up this software to address topics of climate adaptation on a much larger scale. So, firstly, why we need clean energy. I expect you've all seen at least one picture of a drowning polar bear or a polar bear on an iceberg, and I'm sure you've seen at least one dire newspaper headline with respect to climate change. For example, this week, Cape Town is approaching day zero of their water supply, and people are suggesting that climate change was one of the reasons for that. And the prospective impacts are so widespread and so detrimental to vulnerable people in our society that this has been called an issue that will define the contours of this century. So it's a big problem, and it's been described to me before as analogous to trying to swap out the engine of an airplane while it's in flight, because we want people's standards of living to stay the same. We've worked very hard to get to a place where many people have the standard of living that we have, and we want our economy to remain stable. And as we all know, economies aren't necessarily stable, naturally speaking. So renewable energy is a really good solution because it allows new jobs and new development. It allows energy to still be produced. It keeps the lights on, so to speak, but it reduces carbon emissions, which means we can stop adding to the problems that we know we're going to face into the future. And the reason that offshore wind power is particularly a good solution to this for the UK is because the UK does not have a lot of land, but it does have a lot of shore in its economic zones. And that shoreline exists on a continental shelf, which means that the water is shallow. And it also exists in an area where it's windy. And this is ideal because the way that you install a wind turbine is by effectively taking a hydraulic ram and slamming down into the ground and then putting a piece of metal there. And that's, many turbines, or offshore turbines, are built like that. It holds them in place. And so this is great. And the nice thing about it is that it does allow the UK to be a research and development leader in this space. And so there are a lot of opportunities right now in offshore wind in the UK, and it's something that people are really interested in. The problems that come from that, though, is that you are genuinely trying to construct and maintain a complex mechanical structure out in the ocean. So if you picture it from the perspective of the people who actually have to build and maintain these turbines, in order to get to work, you have to get on a vessel. You're going out to the turbine. If you're unlucky and the waves look like that, the boat's going up and down, you're probably seasick. And once you get there, there's a distinct probability that you're going to be climbing up to the top of one of those turbines in windy conditions to try to do maintenance on it or to build something. And so the challenges that arise from this are substantial. And in addition, the sort of consequence that comes from being a new field, offshore wind hasn't existed for very long, is that there isn't necessarily a set upon way in which to optimally do these things. It's still up in the air, it's still being experimented with. And this is very interesting from a software perspective because it means that simulation modeling can be very helpful because we can simulate things that haven't been done and see the ways in which they play out to try to reach optimal and better solutions earlier. And the consequence of these complex operations is that the costs are really substantial. I mean, you have a turbine that might be sweeping the area the size of an American football pitch, producing huge amounts of energy, but that particular vessel, it's called a jack-up barge, and those are literally feet that go down into the water to stabilize it so that you can start bringing equipment across. Those are chartered at about 150,000 euros per day. So any day in which you own one of those vessels and it can't get up to the turbine because the wave is too high or the wind is too strong is a very bad day in the life of somebody. And the long-term consequence of that is that offshore wind power is still not competing financially quite where some of the other renewables are, but is hopefully going to get there soon. So the way that our software helps with this is with simulation. So it is written in Python, and there are a few things that in my mind make it very effective at what it does. The first is that we've spent a lot of time talking to people about how they make decisions. So it's an interesting project because generally speaking, you're trying to create an optimal decision, which computers can do very well, but that doesn't give you the right answer about how something will actually play out in the real world. So we need to capture how humans make decisions, and that's considerably more complex and considerably harder to model in computers than the alternative. But we do that. We've spent that time, we've done that talking, and we've built systems code that can capture complex decision making. So in the simulation that you're seeing right now, every ship has logic, and there's scheduling that is intended to represent the ways that you would actually schedule the construction of a wind turbine. So here you can see the turbines going in one by one, and if they turn red, it's because they've been delayed by weather. And this is really helpful because when you are in a space where there are many ways you could go about doing things, so for example, they're going from that particular port over there, but it's not necessarily clear that that is the best port to go from. In many cases, you might have more than one port that you actually could use as your base. Or you could have different types of vessels that are performing that installation, or different combinations of vessels. And this allows us to see what happens if you actually do that. And furthermore, it calculates the outputs of that. So what you might do as a starting point is take the strategy that you think is going to be optimal for your wind farm, and you run it through a simulation like the one I showed you there. And then you look at the outputs, and those tell you, well, where did you lose money? Where were you delayed? And those outputs give you a hint as to what might not be optimal about the ways in which you're going about your wind farm development, which then allows you to strategize. What might you do differently? And so you can try it again with different vessels, or a different port, or different spare parts, or different staff. And you can simulate it until you get to something that you think is close to optimal for your operations. And so there's quite a few pieces of interesting back-end code that enables this. One of them is that we use statistical distributions to handle uncertainty. So you don't have to tell us how long it's going to take you to do an operation, because really you don't know. What you can tell us is a range in which how long you think it might be, and we will run the simulation thousands of times in order to give you an answer that isn't one answer. It's a variety of answers, and that's more informative for people, and it lets them control their risk, which is very important when you have uncertainty playing out, like new technology, like weather. And of course, associated with that are the optimizations that make it possible to run that many simulations and not have it take an exorbitantly long time. And we also look at a historic weather that spans about 20 years. So we won't just run your simulation on one estimate. We'll see what happened if it started the same time every year for 20 years to give you an understanding of the ways in which wind and wave conditions are actually operating on your operations. I told you before that this problem had been described to me as trying to swap out the engine of an airplane. But there's actually a piece I didn't mention, which is that climate change is already happening and is already changing the weather. So when I say that, what I actually mean is it's like trying to swap out the engine of an airplane as it's flying into more turbulent conditions. And it turns out that the software that we've used, that we're trying to use to optimize operations, has a role here too, because what it can help us understand is, well, how much does that actually impact wind farms now? Because the time it takes to actually build and run a wind farm is on the scale of 40 years. Climate change will be there by the time that wind farm is decommissioned. And so your decisions actually, it's not good enough anymore to use historic weather to make your plans. You actually need to make climate adapted decisions. And luckily for us, many, many smart people have thrown many years of their life and many lines of code at this problem, and they've created something called global climate models. And what these do, in effect, is take the entire planet and break it up into grid cells. And in each grid cell, there are equations, often thousands of equations, and those are representing really anything you need to know to look at climate modeling. So those are capturing, for example, what happens when sunlight hits the Earth, the gases you have in the atmosphere and those interactions, the ways in which water will heat and air will heat, and those circulations will move. And you can run these, and they take a very long time to run, and they create a lot of data, but they're effectively a crystal ball that can make predictions about what it might look like with a lot more carbon dioxide in the atmosphere than there is now. And there are some limits to this. I mean, obviously, we don't actually know exactly how much carbon dioxide there will be in the atmosphere in the future. That depends on us. And there are also some aspects of it that you can't really capture on the scale of the grid cells they use, because it takes too much data to run tiny grid cells, but some of the processes that are incorporated can't be fully captured. So like cloud formation, for example. So there is a process by which scientists have to estimate how to infer how much cloud cover there might be, for example, on a larger scale than what they actually need to model it. And so what you in fact get are something called ensemble models that are giving you a range of possibilities for what the future might look like, which in our case actually works quite well, because we already deal with uncertainty in the work that we do. We already know how to communicate to people what that means. And the outcome of this is one particular global climate model, looking at precipitation, is we get maps like this that show you how much we expect things to change. And that allows, at a first pass, us to screen, to identify locations that are likely to have climate impacts. And it also allows us to run more detailed models. So effectively, what you can do, because we don't have, those grid cells are quite large, is you can run a second set of code, which more or less are putting smaller grid cells in the areas that they care about. And you drive them with the outputs from these global models, and that lets you answer in some cases, very specific questions. So for us, if we want to know for our wind farm what the wind and wave might look like in the future, we're going to run, firstly, a model with smaller grid cells in Europe, for example. We're then going to run wave modeling to convert the wind and atmospheric pressure into wave predictions. And then we're probably going to have to run another model to understand exactly what happens as those waves hit shallow water at an even smaller scale, sometimes, depending on what you need. But once we've done that, we get a set of data that's actually no different from the 20-year historical data we were already using. It's just climate adapted. And that means that all of the software that we have now can in fact be used to answer these questions. And that's what we're doing. We're collaborating with others to create maps for to use our models and put them in a variety of locations around Europe and give people an indication of what the differences in wave conditions that we expect and the differences in wind conditions and current conditions might actually mean in practical terms for offshore wind farms that are operating now and into the future. And it's not just us. These global climate models have created what's effectively an ecosystem of models, looking at everything from the ways in which changes in temperature will affect endangered species and the ways in which trees, etc., are changing, or the ways in which particular species are moving, to what happens when you have more frequent or more extreme storms, and how economies recover from that, and where governments might want to put their funding to allow their economies to rebound as quickly as possible and make sure that humans are affected for as short a time as possible, who they need to protect, how they need to protect them. And so today, code is actually forming a very critical piece of this very difficult problem. And hopefully you can see that collectively what that means is that we have the headlines, the newspaper headlines and political statements do in fact break down into concrete problems. And those concrete problems are being solved by a wide variety of scientists, engineers, and software developers. And code is playing actually a tremendously critical part. So the work of, and it also creates lots of very interesting and cool jobs for people like me. Thank you.